Okay. Yeah, so last time we showed that G tilde is surjective and image of F tilde is contained in kernel of G tilde. And this inclusion, image of F tilde contained in kernel of G tilde, tells us that if by the first isomorphism theorem, this G tilde induces a map, which we denote by G bar, from B tensor M mod image F tilde to C tensor M. Yeah? So if there were so this will be a equality if and only if so that is image F tilde is equal to kernel G tilde if and only if G bar is an isomorphism, right? So if it is an equality, then by first isomorphism theorem this will be a isomorphism, and conversely if it is an isomorphism, then that means this that means image F tilde is equal to kernel G tilde. It's not something smaller. If it was strictly smaller, then this will be a surjection, and the kernel will be kernel G tilde modulo image F tilde. Yeah. What we have to show is that this map G bar, which sends an element alpha bar here. Alpha bar, you can think of it as alpha plus image F tilde, if you like, or alpha bar sends G bar sends alpha bar to G tilde alpha. That is the map you get from the first isomorphism theorem. So we have to show that this G bar is an isomorphism. Is that okay? Is that clear, everyone? Any questions so far? Okay. So it suffices to show G bar is an isomorphism. So for that, we'll find an inverse map and show that it is an inverse. Yeah. So for this, we'll define a map theta from C tensor M to B tensor M mod image F tilde and show that it's R linear and it is inverse to G bar. Yeah. So again, to give a map, R linear map from C cross M, C tensor M to any module is same as giving a bilinear map from C cross M to that module. Yeah. So we define this bilinear map. So x comma M, where x is in C and little m is in capital M. We send it to x tilde tensor M plus image F tilde. So we send it to this quotient. Or if you want to put use the bar notation, you put a bar above this. Yeah. So you can also say bar here, which is same as x tilde tensor M bar, if you like. Yeah. So where x tilde is any pre-image of x in B. So remember G is surjective. Yeah. So G from B to C is surjective. Yeah. So given x in C, you can find some x tilde in G inverse x. So you just take any, it doesn't matter. Yeah. So then, of course, since you are making some choice, you have to say why this is okay, why phi is well defined. So you just check, yeah. So if you take two different pre-images of x in B, then you want to say that x tilde and x tilde prime. Then you want to say that x tilde tensor M plus image F tilde is same as x prime tilde tensor M plus image F tilde. Yeah, so their images, so they represent the same coset. Yeah. So first thing, since x tilde, so x tilde tensor M minus x prime tilde tensor M by basic properties of tensors, we know is same as x tilde minus x prime tilde tensor M. But x tilde minus x prime tilde, that is in the they map to the same element. Yeah, so that their difference is in the kernel of G. Yeah, so this is in the kernel of G, but the sequence A to B to C is exact. Yeah, so this is in kernel of G, which is same as image of F. So here we are using it since A to B to C is exact. So here we use the fact that C to 0 is exact. Here we are using exactness at P. Okay. So we get this is same as, so there exists A in A such that FA is X tilde minus X prime tilde. And so this tensor, there should be a bracket here, X tilde minus X prime tilde tensor M is same as F tilde of A tensor M. Yeah, because this is same as FA tensor M, and FA tensor M, remember, is same as F tilde of A tensor M. So that is how the map was defined. If you recall, defines a map. Yeah, so I haven't written here, but this map sends, last time in the definition we saw this map sends this to FA tensor. So ordinary tensors are sent to corresponding ordinary tensors. Yeah. So hence phi is well defined, and then you also have to check its bilinears. So I think I've checked it in the first variable. Second variable is straightforward, it's because M is R linear, and on the M part is the identity map. So identity map is R linear. So M is an R module, and identity map is R linear. That tells you that it's R linear in the second variable. And for first variable, you just check, yeah. So X plus R times X prime comma M, phi of that is going to be this guy, since the image of X tilde plus R X prime tilde is just X plus R X prime if G of X tilde is X and G of X prime tilde is X prime. Yeah. So you can take you can use any pre-image. So in particular, you can use this pre-image to define phi, and then you just use the property of this little element tensors, the fact that this is a bilinear map, to conclude that this is same as X tilde tensor M plus R times X prime tilde tensor M, and here, of course. So moreover, I should write for R in R and X prime in C. And this is what, and M in capital. We get this. So this proves it's linear in the first variable, and hence it's bilinear. So now by our definition of tensor product, there exists a R bilinear map theta from C tensor M to this, which sends C tensor M, little c tensor little m to B tensor M plus image F tilde, where B is some element of G inverse C. So I've switched from X to C somehow, I suppose, and X tilde to B. Yeah, it's okay. So now you just look at, so theta is an R-linear map, and we already have a map G bar, and we just check that their compositions are identity, at least on the generator, and hence on whole of it. Yeah. So theta composed G bar evaluated at B tensor M plus image F tilde is theta of G tilde of B tensor M, because that's what G bar is. Yeah, remember G bar of alpha bar is G tilde of alpha. Yeah, so alpha here is B tensor M, and alpha bar is B tensor M plus image F tilde. So theta of G bar this is theta of G tilde of B tensor M, and G tilde of B tensor M by definition is GB tensor M. That is how G tilde on pure tensors look like. And then you just apply theta. So theta of GB tensor M. So you just have to take some pre-image of GB under and B is one such pre-image. So you get B tensor M plus image F tilde. So parenthesis is missing. Okay. So this is what we get, that theta composed G bar is identity on these kind of elements. And similarly, G bar composed theta of C tensor M is same as theta of C tensor M by definition is B tensor M plus image F tilde for some B in G inverse C. Yeah, that's the definition in line previous to this line. And so you get that this is same as GB tensor M, because that's what the definition of G bar of some alpha bar is, and that is same as C tensor. So again, G bar composed theta is identity on these kind of elements, and these kind of elements generate form a generating set. So both of them are identity. Okay. So we have that that G bar is indeed an isomorphism, and that completes the proof. Okay, any questions? Sorry. Any questions so far? Okay, so this shows that tensor is right exact, in the sense that if you have a short exact sequence of R module, it will still remain exact on the right, but it may, but it doesn't say whether it's exact on the left. So actually it is not exact on the left. So yeah. Last time I mentioned it, but today we'll see an example. Okay. So for example, you can take this short exact sequence. Yeah. So Z to Z is multiplication by 2. So so that's an injective map, as we know. I mean, Z is an integral domain. So multiplication by any non-zero element is an injective map. And the quotient is, and the co-kernel is Z mod 2Z, yeah, of this inclusion. So we get this short exact sequence. Now you tensor of Z modules, Now you tensor it with Z mod 2Z, yeah, over Z. So if you tensor it with Z mod 2Z over Z, remember Z tensor Z mod 2Z over Z, so it doesn't change the module. So this is again going to be, the first two term is again going to be Z mod 2Z. Even the third term, remember we did, is going to be GCD of Z mod 2 comma 2. Yeah, so and GCD of 2 and 2 is 2, so you again get Z mod 2Z. Yeah. So you get this this sequence, and of course this can't be exact, right? I mean, just look at all the three terms are Z mod 2Z, so there is no chance of this being exact. I mean, the middle term has to be bigger than the left and right for such a thing to be exact. Yeah, but you can just check that what happens is this right map is I don't know why this is fluctuating. Yeah, so this map is an isomorphism, the second map, and the first map is the zero map. Okay, so it's not injective. Point is, you are multiplying everything by 2, and then you are tensoring it with Z mod 2Z. Yeah, so maybe let's just work out this map. It's a good idea. So Z tensor over Z, Z mod 2, Z mod 2Z. That's the first module, which is isomorphic to Z mod 2Z, but let's just write it this way so that we can see. So on the first factor, it was multiplication by 2. Yeah. So if I take any element here, or a typical element A tensor, some integer A tensor B bar, where B is either 0 or 1, then it will go to 2A tensor B bar, yeah, where because on the first factor is just multiplication by 2. but 2A tensor B bar is same as, so you since it's a Z module, you can pull out this 2, and this is same as 2 times A tensor B bar, and you can push it down on the other side. So this is same as A tensor 2B bar, but 2B bar is always 0 in Z mod 2Z, so this is 0. Yeah, so that tells you that the image of any such element is 0, and of course these generate the whole module. So this whole map is the 0 map. So that proves that this is not injective. Okay, any questions? So usually this tensoring with something is not injective. But there are some modules for which this is okay. So that, like we saw, or you may have seen this in the homework, that if you tensor it with S inverse R, so and then you get something which is so it remains exact because tensoring with S inverse R, where S is a multiplicative subset, is localizing. And localizing is exact. Yeah, so such modules have a name. So we won't study much, but I'll just for general knowledge, I'll define it. So an R module M is said to be flat if for every short exact sequence of R modules A to B to C to 0, the induced sequence is exact. Yeah. So if you do commutative algebra later on, you'll study more about such modules. So, so also in the homework, one of the homework problem was to show that projective modules have this property. Yeah. So projective modules are flat. Maybe there was a hypothesis finitely generated, but that is not really needed. Yeah. So it is true irrespective. So projective modules, free modules, projective modules are flat. And then, as I said, S inverse R is a flat R module. Okay. And yeah, so these are the main examples of flat modules. Okay. So for some special modules, tensoring is exact, but otherwise not. Okay, so I'll relate this Hom and Tensor because I promised. So, but I'm not sure whether we'll use this result. But anyway, let's see this theorem. So it has some meaning in category theory, but I'm not sure how much of category theory you know. So it's sort of saying that tensor and Hom are adjoints to each other. Yeah. So that is what it means in the language of category theory. But in ordinary language, in which one can state and understand here, is that given M and K R modules, then Hom of M, comma Hom of NK. So so set of all R linear maps from M to set of R linear maps from M to from N to K. This so left hand side is an R module that is same as Hom of M tensor N over R comma K. Okay, so this is the Hom tensor duality. And this is isomorphic as R linear, so you can R modules. So maybe one can write this as R modules. So you can see more, not just isomorphism as groups, but as R modules. So everything here is an R module. Okay, so so the proof is not difficult. It's just writing down the maps clearly. Yeah, so just untangling essentially. Yeah, so remember, giving an R linear map from M tensor N to K is same as giving a R bilinear map from M cross N to K. Yeah, so there is a one-to-one bijection because of this uniqueness property and so on. Yeah. So there is a one-to-one bijection from between R linear maps from M tensor N to K and R bilinear maps from M cross N to K. So instead of showing a bijectivity between these two, we can also show bijectivity between these two. And our linearity. So I mean these. So we know what this bijection is. Yeah, given a linear map, you just compose it with the structure map M cross N to M tensor N, and you get bilinear map. Yeah, R bilinear. And given this R bilinear map, it induces a linear map which sends pure tensors to which governs how pure tensors go anywhere in K. Yeah, using this bilinear. And then once you know how pure tensors go somewhere, you know where every element goes, because pure tensors sort of generate the whole module. Yeah. So this bijection is first bijection is very transparent. We'll give we'll show that this R set of this R bilinear map. This is in bijection with R linear maps from M to home of n comma n. Okay, and that will complete the proof.
Yeah, for the next part, you just fix a particular M, and that gives you a map from N to K, right?
Say that again.
Yeah, for the next part, you just fix an M, and fixing that M gives a linear map from N to K.
Yeah. So we'll take some theta here, and we'll show that we'll get a bilinear. Yeah. So given a theta, we'll cook up a bilinear map, and giving a bilinear map, we'll get a. So yeah, if you fix an M, then it becomes it's a linear map in N, and this is how you define the R bilinear. Okay, so this is the definition. So given some element theta here, I have to produce a R bilinear map. Yeah, and this is how you produce it. So this is for all M in M and N in N. And of course, this since theta M is R linear, is theta M is actually a R linear map from N to K. It is linear in N. Yeah, so it's so phi sub theta. This this map we have defined from M cross N to K. This is linear in the second variable, and since theta itself is R linear map from M to home, it is linear in as we vary M as well. Yeah, so that tells you that phi is bilinear. Phi sub theta is bilinear. Is that okay? Yeah. So this is how you cook up from R linear map from M to home NK to R bilinear map. And similarly, we'll do the other direction as well. So now given a bilinear map phi from M cross N to K, or I could have just gone one more step and said, that induces a R linear map from M tensor N to K. Yeah. And so this is, I mean, this is not very serious. Yeah. So this is just reducing one step here. So one should one should think of R linear map from tensor product to K as R bilinear map from M cross N to K. This I mean sort of become ingrained so that there is no errors. Yeah. So there is no really real difference between the two notions. So conversely, now given a bilinear map M cross N to K, we want to produce a R linear map from M to N home N comma K. So of course, so given phi, you cook up theta sub phi. And so what should be that theta sub phi? So theta sub phi evaluated at M, you just declare it to be phi M comma dash. Yeah. So here dash means this is, you fill in the value. So this is a map from N to K. And of course, this is R linear because phi is R bilinear. Yeah. So if you fix any element of M, then it gives you a bilinear R linear map. So maybe this is what Swamedeep was saying. Yeah. So if you fix M, then you get an I linear map from N to K. So that gives you, yeah. So maybe this is what Swamedeep was trying to say. Okay, so theta sub phi is a map from M to home of this, and then you have to check that this is R linear. So so you just check that, so that M1 and M2 be two elements of M. So write this for M1, M2 in M, and R in R. Theta sub phi of M1 plus RM2 is by definition phi of M1 plus RM2 evaluated comma something in N. So I just written dash as a map. You can think of it as this. But phi is R bilinear, so it's linear in the first variable, so it becomes this. Yeah. So you get that theta phi is also theta phi is R linear. Yeah. So both the maps are well defined. So from if you start with theta, you get an R bilinear map, and if you start with R bilinear map, you get theta sub phi, which is a map which is a R linear map from M to home R n comma k. Yeah. So now we will show that it's a bijection. So we'll show that these are inverses to each other, and we'll show that one of them is R linear. In one direction at least it's R linear. That's it. Yeah, that will show that it's an isomorphism. Okay. Okay. So maybe it goes to the next page. Okay, so these are inverses and R linear. So yeah, so first I think I'm trying to show here that is R linear. Yeah. So we want to show that let's say this phi as a function of theta is R linear. So if you take theta 1 and theta 2 in home R m comma home R n comma k, and R is some element of the ring, then phi theta 1 plus R theta 2 is same as phi sub theta 1 plus R phi sub theta 2. This is what we want to show. And that will show that it is the map to the to home R M tensor n comma k is also linear, because this is how it will behave. So you just verify. So phi of theta 1 plus R theta 2 m comma n is theta 1 plus R theta 2 m comma evaluated at n. That was the definition of phi sub theta 1 plus R theta 2. And then you just so remember this home is an R module. Yeah, home R m comma home R n comma k. So this breaks up. So theta 1 is an element, theta 2 is an element of this, and R is an element. So this is same as theta 1 m comma m evaluated at n plus R times theta 2 m evaluated at n. So here you are using that since home R m comma home n comma k is R linear, is R module. One second. Okay, so from there we get that this is equal to phi theta 1 of m comma n plus R times phi theta 2 of m comma n. And since m and n are arbitrary, this says that this implies that phi of theta 1 plus R theta 2 is same as phi of theta 1 plus R times phi of theta 2. Yeah. So that says this map which we defined from home R. So this map from this to set of bilinear maps, and then to this Hom R and tensor n comma k. This is R linear. Yeah, so that's what this proves. Okay. So yeah, so I've written this here. Yeah, so this is R linear. This was not needed. So this proves that this map is R linear, and then we want to show that they are inverses. So you just take the composition of these two. So you start with some theta in this guy, and let phi be phi sub theta, and then you take theta prime as theta of this phi, which we just defined. And then we want to show that theta prime is same as theta. Yeah, so you just this. So for m in m, theta prime of m is theta sub phi of m, because that's what theta prime is, and theta sub phi of m is by definition phi of m comma dash. This is the R linear function from n to k you get, and but phi is same as phi sub theta. So phi m comma dash is phi sub theta of m comma dash, and phi sub theta of m dash is by definition theta of m evaluated at that dash. Yeah, so that tells you that theta prime is same as theta. Yeah, theta prime of m is same map as theta m evaluated. Okay. Is that okay? Yeah. And similarly, you do the composition in the other direction, and you get the R bilinear map you started with. Yeah. So if similarly phi is some R bilinear map from m cross n to k, and theta is theta sub phi, and phi prime is phi sub this theta you obtained, and you want to check that phi is equal to phi prime, and that again is straightforward. So you just check that they agree on m every element m comma n. So phi prime of m comma n is phi sub theta of m comma n, which by definition is theta of m comma n, and theta of m evaluated at n, and theta of m evaluated at n is same as theta sub phi, because theta is theta sub phi of m evaluated at n, and this by definition is phi of m comma n. So that was the definition of theta sub phi of m evaluated at n. Okay, so this proves phi equals phi prime, and hence the claim. Hence the claim. So we proved that these two operations are inverses and are linear. Okay, any questions so far? Okay, good. So yeah, so I guess since I had written most of it today, we went a little fast, and we are more or less done with what I was planning to do. So we can so we can do some examples, or yeah, so maybe so maybe I'll do you have any questions before maybe I proceed to something else? Okay. Yeah, so maybe yeah, so maybe I'll say why so the main objective of introducing tensor product was to relate it to product of varieties. Yeah, so let's just try to build some ground for that. Yeah. So yeah, maybe we can start here. So maybe let's call this a proposition. So if let x and y be affine varieties over an algebraically closed field K, Fi and the field K. So remember, this means that X and affine are irreducible algebraic sets, i.e. X and Y are irreducible algebraic sets. Then first observation is that X cross Y is also an irreducible algebraic set. Irreducible algebraic set is irreducible algebraic set, i.e. an affine variety. So once we have done that, then of course one can ask what is the coordinate ring of X cross Y. Yeah. So remember, X and Y has some coordinate ring. Given any affine variety, it has a coordinate ring which is an integral domain. Yeah. And so one can ask what is this coordinate ring of X cross Y, and it happens to be the tensor product. So that's a bit difficult result, that it happens to be the tensor product of a coordinate ring of X with coordinate ring of Y over the field K. Yeah, so both coordinate ring of X and coordinate ring of Y are K algebras. And if you take, so there are K modules as well. And remember, so this was maybe a homework problem, that if you have two K algebras, where K is some ring, then their tensor product is also a K algebra. Yeah. So it's not just a module, but there is a natural multiplication. So, but this fact is just topological. So maybe we'll prove this today, and next time I'll see if I want to give a proof of the fact that tensor product of two integral domain is integral domain. Okay. So yeah. So first of all, yeah. So X is in some an. Yeah. Some closed subset in an. So algebraic set in an, and Y is in am, and then X cross Y is in a n plus m, and it is an algebraic set is clear, right? So because say X is a zero set of some is Vi, let's say I some polynomial ring, I contained in some polynomial ring in n variables, and Y equals V of J, J some polynomial ring in K y1 to ym. Then X cross Y. So it's pairs A comma B, where A belongs to X and B belongs to Y. So this is same as saying that so the I consists of polynomials in x1 to xn, J consists of polynomials in y1 to ym. So if you consider the ideal generated by elements of I and J in this big ring, so maybe ideal generated by elements of I and J contained in, so maybe, I don't know, should I give a name? Let's not worry about it. X1 to Xn, Y1 to Ym. Then this will cut out precisely X cross Y. Yeah, so this X cross Y is precisely V of the ideal generated by I and J. Okay. So if you take a polynomial which yeah, so if you take something in this ring, in this ideal, then yeah, so maybe there is some argument needed. Yeah, so let F belongs to. So I just say take F in I union J. So it's ideal generated by I union J in some sense. Yeah, in this thing. So F belongs to I union J. So if F belongs to I, then it's some. So you should think of this as a polynomial in n plus m variables now. Yeah, but just that the other variables doesn't play a role. Yeah. So. So if you think in that way, then Vi is just X cross, if you like, AM. Yeah. So if you are thinking of I as in this guy, so no matter what the second m coordinates are, the first m coordinates should n coordinates should be in X. That's what it means. Yeah. If F belongs to I, then F of A comma B is 0 if A belongs to X and no condition on B. Yeah, so that tells you that V of I is X cross AM, and similarly V of J is going to be AN cross Y, and so Vi comma J, or V of I union J, is the intersection of these two, X cross AM intersection AN cross Y. So something which belongs to both of them, and that's precisely X cross Y. Yeah. So it's A comma B such that A belongs to X, and no condition on B for the first part, and this is A comma B such that B belongs to Y. So that is same as saying A has to belong to X and B has to belong to Y. Yeah. So this is what we get. So this tells you that that X cross Y is indeed an algebraic set. X cross Y is algebraic set. And we want to show that this is irreducible. Yeah, so this is where the main topology comes in. So so suppose X cross Y is equal to union of two closed sets. Yeah, so F1 union F2, F1 and F2 proper closed sets of X cross Y. Yeah, proper closed subsets of X cross Y in the subspace topology. Yeah. So now let's look at So F1 and F2 are in particular closed in in an plus m as well. Yeah, because x cross y is closed in there. Yeah. So now you consider this this set x cross y for x in x. You just look at the set. Yeah. So you're looking at so maybe I'll draw some picture. So x is some term here, and so this you think of x and this y, and you're looking at one of these fibers. Yeah. So x plus y is same as y. It's isomorphic to y. Yeah. So it's sort of same as y. We haven't really talked about isomorphism, but whatever, it's like y. So if y is irreducible, x cross y is also irreducible. You can't write it as union of two proper closed sets. Yeah. So so what we get is this is same as x cross y is same as x cross y intersection f1 union x cross y intersection f2. Yeah. But since this is irreducible, one of them must be the whole thing. Yeah. So this implies x cross y is contained in f1 or x cross y is contained in f2. So what we get is that the whole fiber is contained in one of the two sets. Yeah. So what we do is define this x1 to be x in x such that x cross y is contained in f1. So either this happens with any element in x, if this doesn't happen, it has to belong to this set. Yeah, x in x such that x cross y is contained in f2. And the previous thing what we showed is says that either x has to belong to any element of x either belongs to x1 or x2. Yeah, hence x is x1 union x2. But x is also irreducible. Yeah. So if you prove x1 is x1 and x2 are closed subset, then one of these x1 or x2 must be x. And if say x1 is x, then that tells you that f1 is basically whole of x cross y. Yeah. So if we show x1 and x2 are closed, then xi equals x for some I, hence I, and if for that I, fi will be equal to x cross y. Yeah, and that will contradict the fact that both f1 and f2 are proper closed subsets of x cross y. So we would have proved it's irreducible. So now let's just check why is x1 closed. So yeah, so let's see.
By definition of saturated closed sets, right? Saturated closed set has to be, the projection has to be saturated.
Yeah, I don't want to, projection is not a good idea to look at, so I don't want to, but maybe saturated, but yeah, so maybe I can write it as some clearly some closed set. Yeah, so Yeah, so those things, so I'm looking at those fibers which are contained in F1. Yeah. So, yeah. So, so some F1 is some subset here, some closed subset, and okay, so maybe I can intersect it with something. Yeah. So yeah. So I want it in X. Yeah. So okay.
Fix
So
a little y in y and then intersect with x cross y. That's the same thing as the projection.
so maybe one has to use projection. Yeah. So little y in y. Yeah. So you just look at the inverse image of that. Yeah. So yeah, x cross little y in y. So x cross y intersection F1. Yeah. Yeah. So yeah. So basically, you are looking at so this is what will this contain? So you take y in y and x here. So if you intersect with F1,
I mean, this has to be all of x, x1, because this is closed.
this has to be all of x1, y.
Yeah. Not all of x1, all of x cross y, because this is closed, right? One is closed, x cross y is closed.
This is
either empty or all of x cross y. Because
so
there's a partition. X cross y intersection F1 and x cross y intersection F2. That partition is x cross y, right?
Yeah, yeah. So x cross y intersection F1, and we have x cross union x cross y intersection F2. This is whole of x cross y. Yeah.
Yeah, yeah.
And okay, so here we can use the fact that x is irreducible.
Yeah.
Yeah. So this is what was missing. So this tells us that x cross y is contained in F1, or x cross y is contained in F2. Yeah. So what we do is consider the intersection. So this is a closed subset. So so x so if x cross y is contained in F1, then what?
Then all since one x coordinate is in F1, then all the pairs x comma little y coordinate will be there. So, because all the fiber is there.
Yeah. So say x cross y is in F1, then we will get that. Yeah, so that tells you. So this, yeah, so maybe this implies. So maybe this thing was not needed. Yeah. So what we get is that x comma y. No, so it only means that some element is in there, but
yeah, but then you can fix the x coordinate, and for any y coordinate, the x comma any y coordinate will be in F1, right? Because all the fiber is there. So this means for all x,
so maybe this is
y is in F1. Yeah.
So x1 is precisely intersection of x cross y intersection F1. So the point is, if x cross y is so maybe this is contained in F2, F1 is not important, but if you look at this intersection, then so if x belongs to x1, then x comma y belongs to F1 for all y. So this containment is clear. Yeah. And if something is in this intersection for all y in y, then of course the other containment is so if some pair and you, okay, so you have to project this onto, yeah, so maybe,
yeah, best to write it. I mean, best to write it just element wise instead of set theoretically.
Yeah. So
I mean, can I just suggest it?
Best to write it element wise. Yeah.
Yeah. So what I mean is you have capital X cross little y contained in capital F1. So that means for all little x in capital X, little x comma little y belongs to F1, right?
So this containment implies for all
little x in capital X, little x comma little y is in F1.
Capital X. Yeah. Little x comma y is in F1.
Yeah. So now that implies, since F1 is saturated, that implies for all x in capital X, for all little y in capital Y, x comma y is in F1. Since for single y it's there, for all y's it must be there as well.
No, that's not the conclusion of this. Yeah. So
of course, right.
No, see, if one point on the fiber is there, that doesn't imply that the whole fiber is there. What it says, so it may happen that F1 and F2 may intersect. Yeah, we are not saying that F1 and F2 are disjoint. You see what the problem is. One point is in F1 doesn't imply that the whole fiber has to be in there.
Yeah, all right, 1 second.
Yeah, so but yeah, so we want to show x1 is closed, but maybe we can use some sort of yeah. This is something is missing. Yeah. So this means this is maybe this is not what we should do. So so you fix a y, x cross y. Yeah, so let's see, x cross y is in F1, and we take the intersection. Yeah, so F1 is some closed subset. So x cross y intersection F1 is certainly closed. And so x cross y is something like this. We intersect with F1, it is closed. And so if we take the intersection of all this as y varies, yeah, then what do we get? So this is same. This should be x1 cross something. X1 cross y. Yeah. Yeah, so this is x1 cross y. No, this is not, so we are not x1 cross y, but yeah, so if we take intersection as y varies, it doesn't make sense. So I mean, what I mean is you have to take the projection of this onto x1. Yeah, so yeah, so yeah, so so this is closed, and yeah, so maybe this is how we'll do it. Yeah, so consider this map x to x cross y, sending x to so now the projection map. Then yeah, I don't want to do the project. So image of a closed set need not be closed under projection map. So that's not what I want to do. That's why I didn't want to use the projection. But so this is going to be something, and yeah, okay, I got it. Yeah, so consider this map x2 x cross y, which sends x to x. So maybe call this map iy, yeah, x comma y. Okay, so this yeah, so this one has to show is continuous in the Zariski topology. Okay, so there is something missing, but this is okay. So this is more believable. So this is not difficult to show that this is continuous. So you look at Iy inverse of x cross y intersection f1, yeah, and you take the intersection. So this is going to be a closed set because x cross y and intersection f1 is closed. So it's going to be a closed set in X, and you take the intersection of this as Y varies. Yeah, so that is precisely X1. Okay, so so maybe this is not needed. Okay. Yeah, so maybe I'll complete the argument next time since we have gotten over time. But this is X1, and since its intersection of arbitrary intersection of closed sets is closed, X1 is closed, and similarly X2 is closed. X2, which is intersection of, I don't know, the other map. Similarly, X2 is closed. Okay, so this is the argument. Okay, so sorry for going over, but yeah, that's the proof. Okay, so the only thing remaining is to check that Iy is continuous. Yeah, so once you know that Iy, this map going x to x comma y, is continuous, then you are good. So so I'm saying one has to check this continuity because you know the topology is not product topology. It's so there is Zariski topology on this one, Zariski topology on this one. So there is some check one has to do, but it's not difficult check. So you get that this inverse image Iy inverse of x cross y intersection f1 is a closed subset. And now if you intersect as y varies, then you get precisely x1 because any element if x belongs to x1, then this for every y in y, x cross y intersection f1 Iy inverse will x will belongs to this guy, and conversely, if x belongs here, then you can show that it belongs to x1. Okay. Okay, so just think through this. This identity works. And, that completes the proof. Any questions? Okay, so maybe you think about it. If it doesn't work out, maybe next time I'll explain why again why x1 is closed. Okay, so maybe I'll stop here.